Hello and good afternoon, everyone. Today, inshallah, we will go through our last lecture through our program. This is the 13th week, quadratics and the classification related to this part. We are in the linear algebra with programming course, as you know, and I'm very, very happy today that's gonna be our lastest lecture for this semester. As you know, all the course materials and everything related to it, you will find them on Moodle, on Yasmin, and also, of course, the notes and the references of our, the recorded lectures, you will find them on YouTube from the beginning of our course till the end of our course to this part. Today I'm going to talk with you about a very nice and a very simple topic, which is quadratic forms. We already know the tools to go through this part, remaining just only to see how it's going to be applied. It's really very interesting part, and I've also tried to solve all the previous problems, and this exercises, since this is our last lecture, to be with you. I will start with the definition of the quadratic form. So if A with all the entered values, A of I or J, be a square matrix of order n. The function Q is a linear transform or a transformation from Rn into R. So I will take the coordinates from Rn and I will impose it, or having the image in R on this form. And it's a multiplication of matrices, xt transpose, which is a row matrix. It's going to be a row matrix times A, the matrix with the coefficients of this quadratic form, times X, which is a column matrix containing the variables, either x1, x2, x3, or whatever, up to xn, or xyz if you are talking about 3-line or something. And this is for every x as given in this, in the definition of Rn. And it's called a quadratic form. Okay. The quadratic form is a function formed from Rn into R to his analytic expressions is given by a homogeneous polynomial with n variables of degree 2, as we will see. I believe this example will make it very clear for you the quadratic forms and how we can get it. So if I have this matrix in front of you, it's not a symmetric matrix, it's a general matrix, 1, 2, 3, 4, 5, 6, 7, 8, and 9. For any numbers, whatever the numbers. And if I want to get the quadratic matrix or the quadratic form relative to this matrix, all I have to do is to say that the quadratic matrix is equal to X transpose A times X, which is really very simple. All I have to do is to multiply this guy. So if I'm talking about 3-line, because this is a 3 by 3 matrix, it's going to be X, Y, and Z, which is 1 times 3. Multiplying it by the A matrix given, which is 1, 2, 3, 4, 5, and 6, 7, 8, and 9. And then the result, I will multiply by the column matrix X, Y, and Z. The result will be, if you do this multiplication, you will have the quadratic form. It's really very simple to do. All I have to do is to multiply this matrix, which is 1 by 3, times the 3 by 3 matrix. As you can see, all the dimensions are working nicely, smoothly. So if I multiply this guy in this matrix, I will have a 1 by 3 matrix. Let's put it here. So I will multiply x, y, and z times 1, 4, and 7. I will be having x plus a 4 over y plus a 7 times z. Then, for multiplying the first row with the second column, I will have a 2 of an x. Here we go, x times 2, plus y times 5, plus 5 over y, plus z times 8, which is going to be 8 over z. And finally, I will multiply x, y, and z times the last column, which leads to 3 of an x, plus a 6 over y, plus 9 over z, and that's the matrix, which is 1 times 3, multiplying it by x, y, and z once more. It will make, multiplying the first element by x, you will have x squared, 4 over an xy, plus a 7 over z by x, multiplying the second by y, you will have 2 over xy, then you will have 5 over y squared. I can write it here. That's a 5 over y squared. Then multiplying 8 over z times times y, you will have 8y and z, and so on for the last component, multiplying 8 by z. As you can see, I will have a quadratic form. So it's really very simple once you have your matrix, you can get the quadratic form assigned to it. This is how we can get it simply when we have the matrix. Okay, let's see it on the slides. It's really very simple. So once more, if I want to get the quadratic form that's related to R3 into R associated with this matrix, all I have to do is to multiply x, y, and z by this matrix, and the result will be multiplied by x, y, and z. It's very, very simple. Multiplying and adding with simplification, you will have this matrix, which is a quadratic form. You have the x squared, y squared, z squared, and also you will have the terms based on this matrix, the A matrix, of x and y, y and z, z and x, and so on. So that's the quadratic form relative to this matrix. In general, by the idea, in general, if R n into R be a quadratic form, so there is a one and the only one symmetric matrix. And that's the type of matrices that we are interested in. Having the symmetric matrices, it's working on, as you saw previously, on a matrix that was not a symmetric matrix. But if I have symmetric matrix, I will be able to get u of x to the power of t times a times x, and I will be able to get the quadratic form. Either getting the matrix from the quadratic form, as you would see, or getting the quadratic form from the matrix if it's given. So once more, if I have this example for the one, okay, 3, 5, and 3, 5, 7, 5, 7, and 9, but this matrix is a symmetric matrix. By the idea, for the symmetric matrices, I can evaluate the quadratic function or the quadratic form very quickly, even without the multiplication. All I have to do for the x, y, and z, I will start with the elements 1, 5, and 9. So I will start 1, it's gonna be the coefficient of x squared, so it's gonna be 1 times x squared. Then the 5 will go with the second element, so it's gonna be a 5 times y squared. Then I will have 9 times z squared. 9 times z squared. Then plus, I will multiply 2 with, this is the situation with symmetric matrices once more. It's not going to be applied on the first matrix that we dealt with in order to get our quadratic form. But it will be very useful with symmetric matrices, as you can see. So all I have to do now is, this is the x, y, and z. So this element, first x times y, that element is going to be the coefficients of x times z, and that's 4y times z. So simply, I can multiply this value by 2 times xy. So it's going to be 6 over xy plus a 10 over xz, and then 14 times y and z. If you remark, that's the quadratic form assigned for this symmetric matrix. So once more, it's an x squared, here is x squared, 5y squared, here is 5y squared, 9z squared, that's a 9z squared. Then you will have 6xy, as you can see, 10 of xz, here you go, and 14y. The nice issue about the symmetric matrices is also I can get the matrix out of the quadratic form if it's given. So if I have the quadratic form, I can quickly write the matrix. See how I'm going to do it. So if this is x, y, and z, I can write the 3 by 3 matrix really very quickly for specifically or especially the symmetric matrices. I can get the symmetric matrix assigned to this quadratic form very quickly. Considering x, y, and z, the elements x squared, y squared, z squared. So all I have to do is to take the coefficients of the squared elements and it will go on the principal diagonal. So it's gonna be a 1, then I will have a positive 5. Of course, I'm keeping the sign, and this is positive 9. So if this is negative 5, this value or this entry is gonna be a negative 5. Then I will go for the elements x, y, the element x, z, and the element y, z. Go for x, y, that's the element of x, y. Divide this value in 2 with the same sign, positive, positive, negative, negative. So it's gonna be a positive of a 3, and also on the 2, 1 element, it's gonna be 3, it's gonna be 3. For xz, I will take the value of 10 divided by 2, putting half in xz and the other half in z of x. So these are the values as you can see. For y and z, which is 14 divided by 2, putting the 7 in yz and the 7 in z and y, and now I have my matrix. If you look to both matrices, you will find them exactly the same. That's the beauty of symmetric matrices and the relation between it and the quadratic forms. They are deeply connected to each other. And as you can see, either having the quadratic form and they want to have the matrix, or having the matrix and getting the quadratic form, both of them are really very simple and accessible for all of us. It is a symmetric matrix, as you can see, exactly as we do. Okay, there is a one-to-one correspondence between the quadratic forms of Rn and the symmetric matrices, and that's what we discovered in the previous slide. Now I want to talk with you about the classification on the quadratic forms. This part is really very important. It's gonna have a lot of applications in the part in calculus 2, where you start maximizing or minimizing certain function. You may be interested in maximizing profit or maximizing revenue for your company or something, or decreasing the costs of, as I told you, of one of your companies or industries or something like this. So all of us is seeking for optimality, so this is gonna be very useful at that part, especially with the multivariable functions as we will see in this part. And it's related to linear algebra, of course. So if I have the quadratic form that I have, q of x with all the elements is greater than 0, then the quadratic form is gonna be greater than 0 for every x belongs to Rn except at 0, and this is the shape that I will have, and it represents a minimum point, and the more analysis will be needed down the road in the part of calculus. But for the time being, I can identify that's a positive definite function. This is a positive semi-definite functions of a quadratic form for this classification. So q of x is greater than or equal to 0. Sometimes q of x will give you positive values, and maybe you will have zeros, and this is for all x belongs to Rn. Now I'm moving to the negative side, or the negative definite, which develops, of course, a maximization point regarding and compared to the neighborhood, and this will happen. It's the inverse of the first relation that we saw. That's q of x is less than 0 for every x belongs to Rn except the 0, of course. Or semi-negative definite, or the negative semi-definite quadratic forms. This will happen when q of x is less than or equal to 0 for every x belongs to Rn. Or the indefinite, or the saddle, they sometimes call it like this, where you have q of x is greater than 0, and this is for some points, and the q of y is less than 0 for the others. Okay? And that's what's called the indefinite quadratic form. So, for example, if I have this quadratic form, which is x squared plus 2y squared, I can easily put it in a symmetric matrix. I don't have the xy element, so its coefficients will be zeros. So I will take 1 for the 1, 1 element, and the 2 for the 2 by 2. And then, since we are missing the next term, which is x and y, the coefficient is going to be 0. I will put 0 over 2 and 0 of 2. That's the matrix that we are dealing with. If you remark, For this matrix, all the elements on the principal diagonal are positives, and so it will be greater than 0 for all the values of x and y except the 0 point. So it is a positive definite. So if you try 1 and 0, 1 and -1, you will end up having positive values, as I'm giving you an example of the substitution in the quadratic form. This is why it is a positive definite. If we tried another matrix, which is x squared by itself, it is missing the xy and the y squared term. So just only the element or the coefficient in front of x squared will be in 1 and 1. The element of y squared doesn't exist, so the coefficient is 0. While the elements of x and y also missing, so it's gonna be zeros. And if you remark for this guy, you will have the values either greater than 0 or equal to 0. And this is actually what happens if you tried 1 and 0 and 0 and 1. You will have positive values or 0. We can call it non-negative values, which is positive, contains the positive and the 0, which is positive semi-definite. On the contrary, if I have negative x squared minus y squared, then the coefficients of x squared, y squared will be both negative, and missing the mixed term of x and y, so you will have zeros, and all the values coming from this quadratic function is going to be in the 0, so you will end up having a negative definite function. In a similar manner, if I have negative y squared, I'm missing the x squared, exactly in a similar manner, so it's going to be a 0 in x squared, negative 1 in y squared, while with the mixed elements is going to be zeros, as you can see. So for all the values, it's going to be less than or equal to 0, which is a negative semi-definite. Sometimes I will have mixed coefficients, like this guy, for example, x squared minus 2 over y squared. Also missing the mixed term, so which makes it very, very simple to see this symmetric matrix, 1, -2, and 2 zeros, which have the positive and the negative points, as you can see. And so the quadratic part is positive in a part of the quadratic part values for some points of x and y will give you a positive feedback or a negative feedback, which means that you will have indefinite type of a quadratic form. Also works for this one, x squared plus 5x squared plus y squared. If you take the coefficients, I can form it 1, 1, 2, and 3, or 2.5 and 2.5 if it is a symmetric matrix we are dealing with. So you will have the following: 1 and 0 will give you positive values, negative 1 and 1 will give you another negative sign, so it's also indefinite. That's the classification of the quadratic forms. We need further investigation to be able to classify my quadratic form if it is a positive definite, negative definite, semi-positive definite, and so on. By the idea, I can go by the abbreviations. So BD stands for positive definite, BSD, which means positive semi-definite, or ND, which is negative definite, MSD, which is negative semi-definite. We can use these abbreviations. Okay, so once more in this slide there is a remark that every positive definite or negative definite, it will need to or contains the positive semi-definite or the negative semi-definite within it. Okay, so it satisfies this relation. In order to make your life easier, I've wrote those couple of lines to make it easier and rememberable for you. Easy to remember. So every positive definite BD matrix is automatically, it's gonna be a positive semi-definite. But the reverse is not correct. So if you have a semi-definite, it's not gonna lead to a positive negative case. This is why, simply because the positive definite, all eigenvalues, if we are talking about the eigenvalues of the quadratic form, is going to be greater than 0. For the positive semi-definite, you may have greater than or equal to 0. Some of the eigenvalues will be greater than 0, and the others will be zeros, as we see down the road. And so BD is a stronger condition than the positive semi-definite. We can say that the positive definite leads to a positive semi-definite, implies, or negative definite implies negative semi-definite. And this is the remark for this slide. Now I'm talking about the principal minors and how to use them to classify your quadratic form if it is a positive definite, positive semi-definite, and so on. So in order to get the leading principal minors, this is really very simple, and also no extra informations. You're already familiar how to get the minors. So if I'm talking about a matrix like this with an n by n rows, I can get the following collection of submatrices of A. This is the matrix, okay? That's the matrix with dimension 1 and 1. That's the matrix with dimension 2 and 2. And I can increase a row and a column every time. So A1 is the matrix of dimension 1 and 1. A2, it will take the elements of the principal diagonal till the second element. So it's gonna be A11, A12, A21 and 2 and 22. Also A3, if you wanna write A3, it will take the elements A11, A21, A31, and so on till you get A33, and so on till you reach AN, which is gonna be within dimension. If I got the determinant of the first matrix, the determinant of the second matrix, the determinant of the third of the AN matrix, those are called the leading principal minors. So once you hear the leading principal minors, this is what we need to do, is to get the minors or the determinant of the matrices on the principal diagonal, as I told you. This is delta 1 or matrix 1. That's gonna be matrix 2, 3 by 3 is gonna be matrix 3, and so on. We will see examples on them shortly in the coming slides. So that's mainly, I will need to evaluate the principal minors in order to help me with the classification. This proposition slide, or this slide, actually will lead you or guide you when you will have a positive definite, a negative definite, and indefinite mainly cases. And of course I can get from the positive definite the case of the positive semi-indefinite, or from the negative definite the case of the the negative semi-definite, just only when you have equal to 0 values. So let Q a quadratic form from Rn, from the n dimensions, either R3 or R2 or Rn, into R, a quadratic form, by the form of x t times a times x, where A is a symmetric matrix. So I will evaluate the minors or the principal minors, A1, A2, An. Then if for all I, for all the minors, for all of them, from 1 to n, all the minors are greater than 0, then you will have a positive definite. Okay, if you have, remark, A sub I times negative 1 to the power of I is greater than 0, which means you will have an alternating case, starting with the first minor less than 0. So the first minor will be less than 0, negative value, yeah, times negative 1, so it will be positive. The second one, A2, it's gonna be a positive times a positive sign, so the result completely will be greater than 0. In such a case, you will have negative definite. If there is an I belongs to I in such that AI, this condition is broken, the order is not correct, or the values is not correct, is not matching with this, then you will have indefinite values or indefinite type of a quadratic form. In order to make this more clear for you, by the idea, this is called Sylvester's criterion for the using the leading principal minors. So the classification simply, also as it is, the positive semi-definite or the positive definite will happen when all the determinants is greater than 0, all the principal diagonals, the principal minors, I'm sorry. Positive semi-definite if they contain zeros. Negative definite if starting the alternation with delta 1 is the determinant, the value of the determinant of matrix A is greater than 0, while the value of the determinant of the second is greater than 0, and so on. So it's an alternating case. Starting with the negative sign, you will have a negative definite. If one of them, this relation is already exists, and one of them is equal to 0, then you will have a negative semi-definite. If none of this, then you will have indefinite case. So if you remark for these examples, the first of them, the example is 2, 1, 1 and 2, which is for a matrix 2 by 2. The first determinant, or the determinant of the first matrix, is going to be 2. The determinant overall, which is a 2 by 2, is going to be 4 minus 1. So delta 1 and the delta 2 are greater than 0. So this case is a positive definite. Okay, if I get for this case, it's 1 times, the first is positive, and the general case is equal to 0 for the delta 2, so it's a positive semi-definite. And here, the first determinant is negative, this is what I told you. The second is positive, so it's going to be a negative definite. If one of them is equal to 0, then delta 2 is equal to 0, but with the same condition, so it's going to be a semi-definite. I've also tried to go through them in depth, step by step. So that's the first matrix. This is the determinant of the first one. This is the determinant overall. Both of them are zeros. This is greater than 0. That's greater than 0. So you will end up having a positive definite. Of course, this is the second case with a positive semi-definite, because the determinant of the first determinant and second determinant are greater than 0 or equal to 0, so it's a positive semi-definite. That's the case when you have the condition that the first determinant is negative, while the even determinant is positive. See, the first determinant of the first matrix is negative 4, negative 1. While negative 4 times negative 1, positive 4, minus 0, so the second is positive, which means you will have a negative definite case. If one of them is equal to 0, like this case, you will have a negative semi-definite. And I want you to remark, if I have this rule broken, or the first is broken, it's going to be indefinite matrix, of course. That's the classification also in front of you for each one of them. And I believe I've already sent you those slides for you just to go through. Another example for this matrix, I will evaluate the principal minors. For this matrix, the principal minors for delta 1 is going to equal to 1, because this is the first matrix. Delta 2, it's going to be 1 times 1, which is also positive to positive 1. If I'm getting delta 3 for the whole thing, so according to Charles' rule, multiplying those numbers is going to be 1, then I will have 0, then I will have 1, so the result is 2, minus the secondary diagonal is 1, so the result overall is 1. This is 0 and that's 0, so also is equal to 1. All of them is greater than zeros. All of them is greater than zeros. So the first case is a case of a positive difference. That's for delta 1, that's for delta 2, and that's for delta 3. So it's a positive difference. Okay, while for this matrix, for example, the first element is positive. The second element, 1 times 1, is 1. Minus 4, so it's a negative value. Now the case is broken, or the classification is broken. It should start with a negative, then positive. Now I have a positive, then negative, which leads to indefinite cases. So this is greater than 0, that's less than 0. I don't care about this guy. The case is broken, so I will have indefinite value or classification for the quadratic form assigned to this symmetric matrix. In a similar manner, he is giving you here, if AI is equal to 0 for certain I belongs to In, then just knowing the leading principal minors of a symmetric matrix is not enough to classify your associated quadratic form. That's if you have one of the deltas equal 0. So I can stick to this truth and consider just only for the principal minors the cases of positive definite, negative definite, or indefinite. If I need to do further analysis, I will go to the general principal minors case or study, which is let A be a square matrix of A and let K belongs to N such that this is the from I1 up to Ik. It's a subset from Yn, it's a set of K integers. So consider AI up to K, the submatrices of A obtained. When keeping the rows and columns, I1 and Ik, we emanate it together. And this is how we are going to get the principal minors of order K of a matrix. That's the general case that it will be based on our, or we can build our classification on it. So once more, all I have to do, and the case is like this, if all principal minors of A are non-negative, take once more, if all of them are non-negative, which means positive or zero, then Q is positive semi-definite. If all the principal minors of A or odd order are non-positive, so it's a negative or zero, so you will be dealing with a negative semi-definite. If both of these cases are broken, then you are working with indefinite case. And that's the more general or the more extra step that you will need for classification using the principal minors. This is how it is described step by step. So all I have to do is to get all the minors of even order. If all the minors of even order are greater than or equal to zero, I will continue. I will look to the negative or to the odd minors. Getting the odd minors, okay, I will be in between three cases. If all of them is equal to greater than or equal to zero, then I will have positive semi-indefinite. This is for all the minors, the principal minors. Okay, if the odd minors are less than or equal to zero, then I will have negative semi-definite. If otherwise, then I will have indefinite. So this is the classification if we get the minors, the general minors of orders K1 up to N, as you would see in the coming example. Okay, if the minors, the even minors, are less than zero, other than this guy, so non-positive, directly I will be leading with indefinite case. So that's the case of the classification based on the minors. I believe we need a good example, so let's consider this quadratic symmetric matrix. I will start evaluating the principal minors, and please be careful about K, the first degree, the second degree, and third degree. Here I have a 3 by 3, so I will stop at third degree. There will be nothing else to test. I will start with the K1. The principal minors of order K is equal to 1. The principal minors of order K is equal to 1 are the minors that exist on the principal diagonal, which are -2, -2, and the -3. So that's minor number 1, -2, minor number 2, which is -2, okay, and the minor number 3, the minor of K equal to 1, the rank is equal to 1, so it's going to be -3, all of them let them equal to 0. The second step, getting the principal minors of order K is equal to 2, and this is very important to remark. I will start, in order to get this, with the minors, okay, of 1 and 2. So I will go for the minors. This is from the rank of 2 or 2 rows. So I will start with the first row and second row, eliminating the third row and the third column. So I will get the value of this determinant, which is -2 times -2, 4, minus 4, the result is 0, so it's greater than or equal to 0. Then I will go for the first and the third row. That's the first and third row, which means I will eliminate the second row and the second column. The numbers are -2, 0, 0, -3. Here we go. Evaluating them is equal to 6. Then I will go the next step for 2 and 3 rows, the second and third rows, which means I will eliminate the first and the first column, leaving me with a 2 by 2 matrix. Okay, that's remaining, -2, 1, 1, and -3, and the result is equal to 5, as you can see. This is how to evaluate from K1, from rank of K2, and the coming rank, because this is a 3 by 3, it's gonna be at the rank of overall, so I will evaluate the value of the determinant, which is greater than or equal to 0. According to the previous slide, of course, we will have an indefinite case, okay? Because mainly, if you go for the even order, you don't find them all greater than or equal to 0, okay? You have 0, 6, and the 5, so that's the case, okay? Just a second. If you go for the even minors, all, I'm going to the even minors, all of them is greater than or equal to 0. I will go for the odd case, and you will find that none of them is identified, so it's gonna be an indefinite case, as you can see. This is the second case. All of them are greater than or equal to 0. So I will go for the even, which is the first and the last one. As you can see, they have negative values and the positive values, so it's gonna be indefinite. Tell you the truth, the spectacular way in order to do this classification with a little hesitation, and very direct, is to evaluate, of course, the eigenvalues. Is to do the quadratic classification according to the eigenvalues. This is clear and square, very clear, crystal clear. All I have to do is to, of course, getting a square matrix. The square matrix have an advantage if it is orthogonal. That's its transpose is its inverse. And that's like the eigenvalues that I evaluated with you at the first lecture when we finish the determinant and we start talking about eigenvalues. We were dealing with a 2 by 2 matrices which are orthogonal, so the transpose is the inverse of the matrix. Okay, a matrix is diagonizable by orthogonal matrix if and only if it is a symmetric matrix. Now for this slide, he will go with you into the diagonalization and also the classification according to the eigenvalues. So if you evaluate the eigenvalues relative to the quadratic function, if all of them is greater than 0, you will have positive definite. Non-negative, which means greater than 0 or equal to 0, you will have positive semi-definite. If all of them less than 0, they will be negative definite. If less than or equal to 0, semi-definite. If some values are positive, others are negative, then you will have indefinite case. This is very clear for the eigenvalues. So for example, if I have this matrix, which is x squared, 4 of x, 8yz, and z squared, I can get the symmetric matrix of this guy really very simple, which is gonna be, if you want to get the symmetric matrix, x squared coefficient is equal to 1. I don't have y squared, so it's gonna be 0. Z squared is also equal to 1. I don't have, here I